Today we are going to talk about the dynamics of uniform circular motion. Last time we talked about objects moving in a circle at a constant radius with a constant speed, and that is uniform circular motion. And we found out that the object stays in that circle because of something called centripetal acceleration. And that acceleration always points toward the middle of the circle. What we're going to talk about today is where that acceleration comes from, because it has to come from somewhere. So your homework for tonight are these two questions. A 900 kilogram car moving at 10 meters per second takes a turn around a circle with a radius of 25 meters. Determine the acceleration and the net force acting upon the car. So you should have two answers for this one. And number two, give an example of centripetal force that was not mentioned in the video. So we are going to talk about something called centripetal force today, and I want you to give me a new genius example of where you would see that. So, we know all three of Newton's laws, and they hold in linear situations or in uniform circular motion situations. They always hold. And we know that Newton's first law states that an object in motion will remain in motion at a constant speed and traveling in a straight line unless a net external force acts upon it. So, if we have a string attached to a ball and we're swinging the ball around, something is keeping that ball in a circle. Otherwise, if there was no force acting on that ball to keep it moving in a circle, it would just move off in a straight line at a constant speed. And that is the law of inertia. So this force could be any number of things. In this picture, it's a string pulling on a ball. It is applying a force inward to keep it moving in a circle. If this force were not there, the ball would not change direction and move in a circle. It would just go at a constant speed in a straight line. So it could be a string pulling on a ball. It could be the friction of car tires against the road in a turn. So I'm sure all of you have been on a highway on-ramp or off-ramp that is a great big circle. There is a force there keeping the car turning in a circle. If there were no force there, the car would keep going in a straight line at a constant velocity, and you would get in a car accident. And that's exactly what happens when there's too much snow and ice on the road. And another example of a force keeping something moving in a circle is gravity pulling on a satellite. This is exactly what happens with the moon. So the moon orbits the Earth because there is a gravitational attraction keeping it pulling toward the Earth. If that gravitational attraction were not there, bye-bye moon, we would never see it again. So we call this force that directs the acceleration of an object toward the center the centripetal force. So anytime you have an object moving in a circle at a constant speed with a set radius, there has to be a force pointing toward the middle. And we know from Newton's second law that any force can be calculated finding mass times acceleration. So we can actually find out what the magnitude of this force is by doing a little calculating. So this is Newton's second law. Force equals mass times acceleration. That means if we want to find the centripetal force, we need to look at the centripetal acceleration, or the acceleration pointing toward the center of the circle to keep this object moving in a circle. So when we substitute our equation for centripetal acceleration in to Newton's second law, we get this beauty, which is how we will calculate the centripetal force of any object. So the amount of force required to keep an object moving in a circle is its mass times its velocity squared. And remember, the squared here is only attached to velocity, is not attached to mass as well. And we take that and we divide by the radius of the circle. So looking at this, if you need to apply a greater force on an object going around in a circle, if the mass is bigger. You also need to apply a greater force if the velocity is larger, if it's going faster. And you need to apply a greater force when the radius is small. And you can probably imagine this in your head. We all have the Kents Hill lanyards with our keys on them. And most people swing them around their finger and let them wrap up around their finger. As you do that, that is not uniform circular motion. As you do that, the radius changes. But when the radius changes, something else has to change. The mass of your keys is going to stay the same. But as the radius gets smaller, as it gets close to your hand, the force either needs to get greater or the velocity needs to change. So if the force that you are applying on those keys stays the same and the radius gets smaller, you probably all noticed that your keys start speeding up and they move faster around your finger the closer they get. And that is because of this equation right here. So we can see that the force must be inward by thinking about a ball on a string. So if we draw a force diagram for this ball, we have gravity pulling it down, maybe a little bit of air resistance working against it, and the string is attached here, so we have tension from the string. If we look at the hand there are a lot of complicated things going on with the hand. Gravity is pulling it down. The arm is also keeping it up, the muscles, but the string is also putting tension on the hand, right? You can feel this when you swing something around on a string. You can feel the tension of the string pulling on your hand. And if we look at this object, we know the tension of that string is always toward the middle of the circle. One of the great misconceptions about physics is that there is an outward force, that there is a force acting on this object traveling in a circle going that way. There is no such thing. Most people call this a centrifugal force, and it causes objects to fly out of the circle. This does not exist. It is not a real thing. And please do not get the words centripetal and centrifugal mixed up. Centripetal force is a real thing. It is the force pointing toward the center of the circle that keeps it moving in uniform circular motion. Centrifugal force is a bunch of baloney. So there is no centrifugal force pointing outward. Most people think there is because when the string breaks or when you let go, the object flies out of the circular path. But all this is inertia. We know that an object in motion will stay in motion in a straight line unless acted upon by an outside force. So when you're swinging a ball around in a circle and the string breaks, the ball is not going to fly out to the side like this, right? There's nothing pushing the ball out to the side. What will happen is as the ball is going around and it breaks, if the string breaks at this exact point, its velocity is in this direction. So that means that's where the ball is going to go. This ball has mass, it has inertia, so it wants to continue moving in a straight line at that speed because there is no longer a force acting to pull it into the center of the circle. So I will demonstrate this in class, but when you swing something around and let go of it, the object doesn't fly out to the side, it flies straight off tangent to the circle. Again, I am going to beat this into you because it is a very, very important point. There is no such thing as centrifugal force. If we consider a ball on top of a board, the ball will have linear motion when the board moves forward. And if the board is rotated, the ball will continue its linear motion. So the ball is going this way, and it still goes that way because of its inertia. The board might change direction. It goes up and then it rotates. But if there is not enough friction on this board to cause a centripetal force to keep the ball moving in a circle along with it, the ball is just going to keep going forward. If there's enough friction here, then the ball will stay with the board and move around in a circle. And that friction provides the centripetal force pointing toward the center of that circle. So this all has to do with frames of reference. And we've talked about frames of reference. It's your point of view from which you are observing an event. So suppose that instead of a ball and a board, the situation is you sitting in a car and you get pushed toward the door when the car turns left. So we've all been in a car before, we've all felt this. As the car goes around a turn, you feel like you get pushed to the outside. What in fact is happening is as the car turns, if this is you, and you're moving, the whole car is moving this way, inertia tells us your body wants to continue moving in that direction. So this is you, and your body still wants to go this way. If the car is turning, the reason why you feel like you get pushed to the outside is because the car is moving into you. Until the friction of the seat on your butt or the door pushes you in a circular motion this way, because those things apply a centripetal force, until that happens, you want to keep going in a straight line at a constant velocity. So it seems weird. When you're sitting in a car and the car turns, you totally feel like you are being pushed to the outside. But what's happening is you are staying exactly the same, and the car is moving into you. We have a pretty cool video here that I will show in class. I just want to show you just a brief amount. So we have a little puck, an air puck, frictionless puck, and it just moved around on its own in a circle. What the heck is happening here? Well, you will find out the next time that I see you in class. So your homework tonight is to apply centripetal, not centrifugal, force to these two questions and have them ready to be handed in next time you come to class.